Hello and welcome to another session in real analysis. In this session, we are going to discuss labeling of elements in certain sets. Given a finite set, we can label the elements in such a way that the elements will be appearing in some particular order. For example, suppose that we are given a set consisting of 10 elements. We may label them in the fashion this is first element, this is second element, etc. This is the 10th element. Of course, we can have different labelings possible, but the important thing is we are labeling the elements in this set in such a way that all the elements get exactly one label and no element is left out. This is definitely possible for finite sets. But now, what about infinite sets? Can we find such a labeling or can we define such a labeling for each and every infinite set? For example, consider the set of all even natural numbers. This is an infinite set. Can we put some labeling for the even natural numbers in such a way that every element we would be able to say that this is the xth element or ith element, and every element will be having some label. One obvious labeling is taking 2 as the first even natural number, 4 as the second even natural number, 6 as the third even natural number, etc. Go on like that. If we are labeling even natural numbers in this way, we will be definitely able to say that all even natural numbers will be given one label and only one label. Not that. What are the labels we used? The labels we used are from the set of all natural numbers because first element, second element, third element, that means we are mapping from 1 to that particular element, 2 to that second element, or the element which we want to call as the second element, 3 to the element which we want to call as the third element, etc. So for certain infinite sets, this is probably possible that from the set of all natural numbers, we can define a mapping to the set in such a way that we can label the elements using the natural numbers. So we will say that the first element is x1 equal to this, second element in that set is x2 equal to this, etc. If such a labeling using the natural numbers is possible for one particular set, that set we will call as a countable set. In this session, we are going to discuss the notion of countability in subsets of real number system. This is the concept that we are going to discuss today, countability. A set capital A is said to be a countable set if the cardinality of the set of all natural numbers and A are the same. That is, a set A is countable if N and A have the same cardinality. That is, A is countable if we can find a one-to-one correspondence from N to A. If we can define a one-one onto function f from N to A, we will say that the set capital A is countable. Some obvious examples are the following. A equal to N itself. So in this case, what is the natural choice for f that we can define from N to A in such a way that f is 1, 1 and f is 1, 2? Here we need to define a function f from N to A, which is N to N itself, in such a way that that function is 1, 1 and 1, 2. The natural choice for defining a one-one onto function from a set to that itself is the identity function. Let f from into a equal to n itself be defined by f of n equal to n. This function is easily verifiable that it is 1 1 and it is onto. Therefore, n itself is countable. F is 1 1 and onto, and so n itself is countable. Note that since we want the set to be having the same cardinality as that of the set of all natural numbers, countable set cannot be a finite set. We will have to always take an infinite set to check if it's countable or not. Finite sets cannot be countable according to our definition. Next example, we have already seen this example. We have discussed this example in the beginning of the session that 2n equal to the set of all 2n where n belongs to n, even natural numbers. So how can we define f from n to 2n, which is 1 and 2? The natural choice is to define fn is equal to 2n for all n. So this function, we can easily see that this is 1 1 and odd. So this is left as an exercise and it's very trivial. Now we are moving towards another example. Suppose that we consider a1 equal to n union 0. The question is a1 countable? We know that if we are taking the set of full natural numbers itself, that is countable. That means we can label every natural number by saying that this is the first element in our labeling, this is the second element in our labeling, etc. And no natural number will be left out of our labeling. This is quite possible. But now we have a slightly different set. This is A1 and this is N and 0 taken together. So one possibility is this. We have n to n this function. This is the identity function from n to n defined in this way. 1 to 1, 2 going to 2, 3 going to 3, etc. Now we have 0 as probably the starting element. If we bring 0 to the first position and push everything from 1 to 3 one position rightwards, we will get this 0 in the first position, 1 in the second position, 2 in the third position, etc. So what is this new function that we are defining? The function we are defining from n to a is a modified version of our original identity function. Suppose we call that function as f1 from n to a1. This we can define as f1 of every natural number. See, 1 is going to 0 and 2 going to 1, 3 to 2. So this is n minus 1. So this is a 1 1 onto function that can be verified easily. So the question is to verify f1 1 1 and onto. Suppose that we have a slight modification of the previous example and we choose a2 equal to n union 0 minus 1. So can we still find a function from natural numbers to a2 which is 1 1 and onto, so that we can say that a2 is also countable? We have seen that a1, this is countable. This is countable. So we have answered in the positive sense, this is countable. Now the question is about A2, which is n union 0 minus 1. So how do we define a one onto function from n to this? So given the previous function, now it's going to be somewhat easy. Consider the previous function, which we called as label as f1. F1 we defined as 1 to 0, 2 to 1, 3 to 2, 4 to 3, etc. This is what the range of f1 is. The now, if you want to include minus 1 also, one possibility is to push the 0, 1, 2, 3, etc. one more position to the right side and bring minus 1 to the initial position. So minus 1, 0, 1, 2, etc. So how do we define f2 here? F2 is defined to be f2 from n to a2. This can be defined as we are bringing one more position, we are bringing one more to the left, one is now going to minus 1, 2 to 0. So we are subtracting minus 2, therefore f2 of n is equal to n minus 2 is the definition, and it can be verified that it's 1 1 and 1. So up to here it's fine. So it becomes now obvious that if we are attaching elements like 0, minus 1, minus 2, etc. up to some minus k, where k is a natural number, then all these sets are going to be countable using the function f of n equal to n minus k. If we are having elements up to k, we can define f of n is equal to n minus, not k, n minus of here we have defined 2 minus 2 for including minus 1. Therefore, one extra we have to subtract. Therefore, n minus of k plus 1 or n minus k minus 1 we have to define. So the question is the following. Show that a k equal to n union 0 minus 1 etc. minus of k minus 1 is countable, where k is a natural number. Okay, as far as finite sets are considered, this is fine. Finite sets are concerning, we have done that. Now, we are going to see an infinite number question, infinite number of elements attached to natural numbers, and that is the obvious set z. The question is the following. Is n is z equal to minus 2, minus 1, 0, 1, 2, etc. Countable. We have seen that if we are attaching a finite number of negative numbers, that set still remains to be countable. But here we have infinitely many integers, negative integers attached to n, and including, of course, 0 to get z. And the question is if this new set is also countable. So if we start counting from the least element, see in the previous two examples, we started labeling from the least element. In the case of n union 0, we started labeling from 0, then we label 1, then we label 2, etc. 0 is the least element appearing here. So we started labeling from 0. Here the elements are starting, least element is minus 1. So we label the elements as minus 1 first, the least one, 0, second one, which is the second least one, then 1, then 2, etc. But in the present example, we cannot perform such a labeling because we don't know what is the least negative integer we have here. That's a confusion, that's a problem for us. So arranging them in the starting from the least is not going to work here. Another possible probability is whenever we want to list out all the elements Z exhaustively, One technique most of the times we use is arrange them in the following fashion: 0 plus or minus 1 plus or minus 2 plus or minus 3, etc. That means we are arranging the elements with the least modulus coming first, the second least modulus coming next, etc. So one possible labeling for Z is the following: 0 possible arrangement, in fact, plus or minus 1 plus or minus 2 plus or minus 3, etc. But here now the problem is that of course we can say that 0 is the first element. Then now we have here, if we expand this, 0 minus 1 plus 1, these two are coming in one group, minus 2 plus 2, these two are coming in the next group in magnitude, they are same in magnitude, minus 3 plus 3, they are in same group, etc. Now, if you want to label 0 as the first element, that will definitely go fine. But what about minus 1 and 1? We cannot label minus 1 and 1 both to be the second element. So we have to choose one of the element and we have to mark it as second. So the technique that we are going to apply here, we have actually seen this in one of the previous exercises. That is, mark this 0 as first. The second one and third one we will label from this group, and most probably we can choose the least one in this set. Not that, the least one in this set we are giving the first labeling available after using all the labels up to the last collection. What is the next labeling available? That is 3. So 2 and 3 utilized. Now we have to label minus 2 and plus 2. So for minus 2 and plus 2, the least labeling now available is 4. So 4 we will give to the least element in this particular group, and 5 we will give to the least next element in this particular group. So in the same way we will give 6 and we will give 7. 6 to minus 3, 7 to 3. This labeling actually we formulated in a formula like structure in the following way. We actually defined this labeling from n to z by the following expressions. F of n we defined to be, just see that here it is 1 going to 0, that is n going to n minus 1. Now 3 going to 1, that is 3 going to 3 minus 1, that is not correct. Okay, we will look at one more element. 5 going to 2, we are looking at the positive elements. So if you look at the positive elements, we have taken 1 to 0, 3 to 1, 5 to 2, which is correct, 7 to 3. So if you carefully look at all these things, 3, 1 going to 1 minus 1, that's fine. 3 going to just 1, but if it's 1 minus, if it is just n minus 1, 3 would have to go to 3 would have gone to 3 minus 1, which is 2, but that is not happening. It is going to 3 minus 1 whole divided by 2. Therefore here we are taking n going to n minus 1 by 2. Of course these are all natural numbers, therefore n minus 1 by 2 will definitely become an integer. So this is correct for 5. 5 minus 1 by 2, that is 4 by 2, that's 2. Therefore for odd integers we have n going to n minus 1 by 2 if n odd. And what about even integers? If we observe once again, we have 2 going to minus 1, 4 to minus 2, 6 to minus 3. Therefore, here it is actually the half but with a negative sign. Therefore, n is going to minus n by 2 if n is even, minus n by 2 if n even. So this is the technical function that we use for defining a one-to-one correspondence from the set of all natural numbers to the set of all integers. Now, though we wrote this function in a closed form, we haven't actually verified that this function is one-one and onto. Of course, according to our definition, we have constructed the function in such a way that we will be using one label only once and every integer will be labeled, but still we can probably try to prove it using rigorous mathematical arguments. So what are the things we have to verify? We have to show that the function we defined in this way, that is f of n equal to n minus 1 by 2 if n odd, minus n by 2 if n even, we have to show that this function is a 1 onto function. Next question or sub question is the following. Verify that the above f is 1 and onto. We are going to do that now. To verify that the function f we defined above is 1 and onto, we start with the onto part. So part 1 is the following. So to show that f is onto, what do we need to do? We have to choose an integer from z. Then we have to show that this integer is the image of some natural number in capital N. We have to locate a natural number corresponding to this m. So we choose m in z, and according to our construction, we have defined f to be having two types of formulae. One is n minus 1 by 2 and other is minus n by 2. And what are the results of this n minus 1 by 2 and minus n by 2? N minus 1 by 2 will always give non-negative integers. We can see here 0 corresponding to 1 where n is odd, 3 corresponding to 0 corresponding to 1 corresponding to 3, 2 corresponding to 5, 3 to 7. So here we have all these integers non-negative when we chose n to be odd. So if the m we have taken is non-negative, probably we have to look for an n in such a way that f of n is equal to n minus 1 by 2 equal to m. So we have to divide this part into again two cases. The first case is if m non-negative, second case is if m negative. So suppose m is greater than or equal to 0. So we have to find some k such that f of k is equal to m. To show that f is onto, we have to find a natural number such that f of k equal to m. Now, though we don't know what exactly this k is going to be, we can probably make a guess. Since m is a non-negative integer, m is a non-negative integer, probably this k is going to be, we know that non-negative integer corresponds to n minus 1 by 2. Therefore, we will try to solve for k minus 1 by 2 equal to m and locate a value for k. Since m greater than or equal to 0, uh, it has to be some k minus 1 by 2 with k natural number. We don't know if such a k definitely exists, but we are trying to see if we can find out some k. Remember that we know m and we have no idea about k. But if m is greater than or equal to 0 and if m is equal to f of k, since we know that it must be equal to k minus 1 by 2 for some k odd. That is the only way. So, okay, we will try to solve this. K minus 1 by 2, we have to locate this k. This implies on rearranging k equal to 2m plus 1. Okay, 2m plus 1 is known to us because m is known to us. Now, f of 2m plus 1, what is this? F of 2m plus 1 is going to be equal to 2m plus 1 minus 1 by 2, which is m. So that is done. We located the k. What is our k? K is equal to this is what we located, 2m plus 1. So m has pre-image 2m plus 1. Therefore, in this case, the onto part is clear. Now what is next? If m is less than 0, now we have to locate a k. That is the second part. Suppose now m less than 0. Now, as in the previous case, if m is less than 0, we have to find if it exists, k belongs to n such that f of k equal to m. But m is less than 0, and therefore we can probably guess that m is going to be equal to minus k by 2. So we will solve for that. Since m is negative, f of k is minus k by 2 equal to m, or k equal to minus 2m equal to 2 into minus m. Now m is less than 0, therefore minus m is greater than 0. Therefore, we choose k equal to 2 into minus m, then f of k equal to 2 into minus m minus of 2 into minus m, which is equal to m. So in this case also, we are finding one k in such a way that f of k is equal to that m. Therefore, if m greater than or equal to 0, we can find this k equal to 2m plus 1. If m is less than 0, our k is nothing but minus 2m or 2 into minus m. So in either case, we are getting a pre-image for m, and so f is odd. Now, here's this function 1, 1. The part 2 is the following. How can we show that this function is 1, 1? So for showing a function is 1 or not, the most commonly used technique is to assume that f of n1 equal to f of n2 for some n1 n2 in the domain, and show that in that case n1 must be equal to n2. So we are going to use the familiar route. Suppose f of n1 equal to f of n2 for some n1 n2 natural numbers. So if f of n1 equal to f of n2, then either both these numbers are non-negative or both these numbers are negative. Either f of n1 and f of n2 both greater than or equal to 0, or both less than or equal to 0. So if both are greater than or equal to 0, we have already seen that greater than or equal to 0 happens when we choose n minus 1 by 2, and less than or equal to less than 0 happens when f of n is equal to minus n by 2. So if both are greater than or equal to 0, then f of n1 equal to n1 minus 1 by 2, but this is equal to f of n2 equal to n2 minus 1 by 2. If we solve this n1 minus 1 by 2 equal to n2 minus 1 by 2, we get n1 equal to n2. Similarly, if we have f of n1 and f of n2 both less than, oh, this is not less than or equal to, this is less than. If both are less than 0, if f of n1 F of n2 both less than 0, then we have f of n1 equal to n1 by 2 minus n1 by 2 minus n1 by 2 equal to f of n2 equal to minus n2 by 2, together again implying that n1 equal to n2. So in either case we will get f of n1 equal to f of n2 implies that n1 equal to n2, therefore f is 1. So f is 1 1, f is on 2, therefore f is a 1 to 1 correspondence from n to z, and so z is counted. Z is therefore countable. So this is the next infinite set after n union finitely many negative integers. But the special thing about this set is that we are not attaching or appending or prefixing a finitely many negative integers to n, but here we have infinitely many negative integers, and even in this case we are getting the set of all integers to be a countable set. So set of all natural numbers countable, even natural numbers countable, set of all natural numbers union a few negative, non-negative, zero elements, they are all countable, and Z itself is countable. Now there is a question, show that A equal to 2m plus 1, where m belongs to Z is countable. This is an exercise for you to show that the set of all integers is countable.